Our world runs on ones and zeros digital switches called transistors. This binary language has powered revolutions in technology, science, and daily life. We've made transistors so small they're approaching the size of atoms. But at this atomic scale, the rules of classical physics break down. The familiar logic of on and off, yes and no longer applies. We're hitting a wall, the physical limits of classical computing. Our computers, for all their power, can't fully model complex molecules, climate, or crack the toughest codes. Some of nature's biggest problems remain unsolved. The universe is more than just ones and zeros. We need a new kind of computer, one that speaks the universe's native language, a language of probability, possibility, and connection. To solve the next generation of problems, we must look beyond the classical world. We must dare to build a machine that thinks in a fundamentally new way. The future of computing lies in the quantum realm. This isn't a failure of classical computers, it's their greatest achievement. We've pushed them as far as they can go. Now, it's time to embrace the quantum. The next leap in technology will come from understanding and harnessing the strange rules of the quantum world. We stand at a turning point in human history. The question is, are we ready to take the next step? The journey begins with quantum thinking. Let's see where it leads. The universe hides its secrets in the quantum world. Classical computers can only watch from the sidelines, but what if we could build a machine that uses the quantum world itself? Physicists like Richard Feynman imagined this possibility, a computer built from nature's own rules. To simulate nature, you need a computer that is part of nature. The goal shifted from making smaller switches to inventing a new kind of switch, one that can be both on and off at once. Quantum computing is a radical departure from the predictable step-by-step logic of classical machines. In the quantum world, everything is a cloud of probabilities. Quantum computers can explore every possible path at once. Imagine reading every book in a library simultaneously. This power could solve problems that would take classical computers billions of years. The challenge: how do we control the uncontrollable? Building a quantum computer means rethinking information itself. It's not just about speed, it's about a new reality for computation. The quantum revolution is about to begin. At the heart of quantum computing is the qubit, a quantum bit. Unlike a classical bit, a qubit can be a 1, a 0, or both at the same time thanks to superposition. Picture a spinning coin. While in the air, it's both heads and tails. Only when you catch it does it pick a side. Qubits hold this uncertainty, unlocking immense power. 2 qubits can represent 4 states at once. A few hundred can represent more than atoms in the universe. This is exponential power. Parallel universes of computation inside one machine. But there's more entanglement. When qubits are entangled, their states are linked no matter how far apart they are. Measure one, and you instantly know the other. This spooky action at a distance creates a web of information impossible in classical computers. Superposition and entanglement are the working tools of a new era. Scientists have built real qubits using supercooled circuits, trapped ions and photons. They've learned to control superposition and entanglement, bending quantum rules to our will. Each breakthrough brings us closer to harnessing the universe's language. The magic of qubits is no longer theory, it's reality. We're learning to compute in ways never before possible. The quantum world is becoming our new playground. The possibilities are staggering. We're only beginning to understand what qubits can do. The future belongs to those who master this magic. Quantum computing is here. For years, quantum computers were just theory. Then tech giants like IBM and Google joined the race. The goal: quantum supremacy. When a quantum computer outperforms any classical machine on a specific task. In 2019, Google's Sycamore processor achieved this, solving a problem in 200 seconds that would take a supercomputer thousands of years. The calculation itself wasn't practical, but the proof was historic. Debate and competition followed, pushing the science forward. Now the question isn't if quantum computers will change the world, but when and who will lead. The race is on. Building a powerful quantum computer is a monumental challenge. Qubits are fragile. Tiny disturbances can destroy their quantum state. To protect them, quantum computers are housed in ultra-cold, isolated environments. Even then, errors creep in, and quantum error correction is a massive hurdle. Unlike classical bits, qubits can't be copied, so new methods are needed to detect and fix errors. Quantum software is another challenge. Old algorithms won't work. We need new quantum algorithms designed for superposition and entanglement. Researchers worldwide are inventing these tools from scratch. Taming the quantum beast requires new hardware, new software, and a new way of thinking. The journey is just beginning. As we tame the quantum beast, a new era dawns. Quantum computers could revolutionize medicine, modeling molecules to design new drugs and materials. They could create catalysts to fight climate change and design better batteries. Quantum power could break today's cryptography, forcing us to invent new, secure systems. Quantum communication may offer perfectly secure channels. Artificial intelligence, climate modeling, finance, every field could be transformed. We're still in the early days, but the foundation is being laid now. Quantum computing is more than technology. It's a new way to see the universe. It's a testament to human curiosity and our drive to solve the impossible. The work happening today will shape a world we can barely imagine. The secrets of the universe are becoming our tools. The quantum future is here.